Hi, this is a Calculus 1 problem. We are looking at problem number 13 from the 4.2 section homework. This problem asks us to use the limit process to find the area of the region between the graph of the function and the x-axis over the interval. All right, so we've talked about how you can use, and it's a little bit easier to use in 4.3, the definite integral. However, if we don't have that, we can also use a finite number of rectangles or infinitely many rectangles with limits. That's using the limit process. So let's kind of sketch out over here what we're looking at. So I have from 2 to 4. And I have a curve. And I like to make a table of values sometimes. So 2, 3, 4, just to start. We may have more X and Y's, but let's just start with those ones first. Oops. No, bumped it. I don't want that. Okay, so these are my X's and these are my corresponding Y's. So if I plug in 2, I have 2 to the third, which is 8. 64 minus 8, this is going to give us a 56. For 3 to the third is 27. So 27 minus 64. Sorry, 64 minus 27. We end up with a 37. And then we also can plug in four, which I believe 4 to the third is 64. So we have 64 minus 64. This is going to give us 0. So let's see. So we have 1, 2, 3, 4. This is supposed to be just a sketch. I'm already getting a little bit ahead of myself on a sketch, but so we have 4, 0 as a point. 1 is not on there, but just to give us an idea of the shape of the graph. If we did have 1, we would have a 63, so that's going to be very high on the graph. We'd have 2, we have a 56. 3. And then when X equaled 0, we'd be at a 64, so we'd have the end of this point. So if you think about what this is going to look like, it would look sort of like this S shape, but then it's going to be, not through the center, but through this. So something like this, but we're looking at from X equals 2 to X equals 4. Okay, so we're sort of looking at this region right here. Now you don't have to draw the region, but it can be helpful sometimes to have a visual. And then I like to draw a rectangle so I can see what's my upper bound, what's my lower bound. Well, my width for this rectangle, depending on how many I have, that's my delta x of I. And so my base, which is my delta x of I, is going to be equal to 4. minus 2, that full length, and then we'll divide it by the number of rectangles we have, which we're going to look at the limit as n goes to infinity, where we have an infinite number of rectangles. But for right now, the width of each of them is going to be 2 over n. And of course, the width is going to get smaller when you increase the number of rectangles. We're starting off on the left. And so that's going to start with a plus delta x sub I times I. So in this case, we have 2 plus 2 over n times I. And our height then for our rectangles is going to be my corresponding y value. So that's going to be my f of c sub I. So then we're going to look at the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I times delta x sub I. So this is going to be equal to the limit as n goes to infinity of the sum from I equals 1 to n, 64 minus our c sub I, which is 2 plus 2i over n to the third. And then all of that times 2 over n. So again, that 2 over n you can factor out because it's not our counting index. Our I is the only thing we can't factor out because that's part of our counting and it changes with each term. So we have the limit as n goes to infinity of 2 over n times this sum from I equals 1 to n of 64 minus, I'm going to go ahead and expand and I'll switch colors for you if I can. So we want to expand that to the third power. So that's going to be 2 plus 2i over n times itself, to square it. So we get 4 plus 4 plus 4. We get 8i over n plus 4i squared over n squared. And then we multiply that again by 2 plus 2 over n I. We can then distribute and combine like terms. So I get 8 plus 16i over n plus 8i squared over n squared plus 8i over n plus 16i squared over n squared plus 8i squared over n squared, n to the third, excuse me, and I to the third, n to the third. Okay, so we should have 3 times 2, we should have 6. We do have 6 terms. And then we can simplify and combine like terms. This is going to be 8. This 16i over n plus 8i over n is going to give me 24i over n. And then 8i squared over n squared adds to 16i squared over n squared. That's also going to give us a 24 I squared over n squared, and then we have plus 8 I to the third over n to the third. So we can go ahead and substitute that back in here. So I have minus 8 plus 24 I over n plus 24 I squared over n squared plus 8 I to the third over n to the third. Okay, let's kind of zoom in there. Lots of error for lots of opportunity for algebra error and arithmetic error. So hopefully you're following along and hopefully catching me if I make any mistakes, because that's bound to happen, even though I wish it didn't. So then we distribute. So over here we've got the limit as n goes to infinity of 2 over n, 64 minus 8. That's going to get us a sum from I equals 1 to n of 56. And then minus the sum from I equals 1 to n. We can factor out a 24 over n, not that it really makes a difference, but 24 over n times I minus the sum from I equals 1 to n of 24 I squared over n squared, and then minus the sum from I equals 1 to n 8 I to the third over n to the third. We can distribute, but I'm going to wait just to distribute that 2 over n, and I'm going to complete each one of these summands. So the limit as n goes to infinity, 2 over n. This first summation, the sum of 56 from I equals 1 to n, is just going to be 56 times n. The sum of I from I equals 1 to n will have the minus 24 n out front. That's just a constant, but the sum of I from I equals 1 to n is going to be n plus or times n plus 1 all together over 2. And then here we have really just the I squared, the 24 n squared, that'll stay out front. We have minus 24 over n squared. And then this is going to be n times n plus 1 times 2n plus 1 altogether over 6. And then this stuff over here, I might have to erase it just because I don't want to get it. Hopefully you wrote that down. It's going to get in the way. Okay, and then the last one is the I to the third. So we have this minus 8 over n to the third. And we have I to the third. The sum of I to the third from I equals 1 to n is given by n squared, n plus 1 squared over 4. Finish off our parentheses. We've got a lot of things that we can simplify. Some things that don't. Yeah, just like I said, lots of room for human error and arithmetic error on some of these problems. So we have 2 over n. Now let's go ahead and cancel some things. So n will cancel. This will become a 12. That 2 will cancel. Here 24 cancels with 6. We have a 4 n, this becomes for n, 8, n squared, this is n. We have 2. Okay, so after simplifying, we have this 56n minus 12 n plus 1 minus 4 over n plus 1, 2n plus 1 minus 2 over n plus 1 quantity squared. And we'll simplify, continuing the limit as n goes to infinity. 2 over n, 56n minus 12n minus 12 minus 4 over n, multiplying n plus 1 by 2n plus 1. We get 2n squared plus 3n plus 1, and then minus 2n, foiling or expanding that n plus 1 quantity squared becomes n squared plus 2n plus 1. And there we have the limit as n goes to infinity. 2 over n, 56n minus 12n. We can combine those, I suppose. This is going to be a 44n minus 12 minus, here are the n's will cancel. We have minus an 8n. We'll have minus 12 minus 4 over n minus 2n minus 4 minus 2 over n. From there, this becomes the limit as n goes to infinity. Distributing, well, I guess we could combine like terms and then distribute. Kind of just getting to the end, just kind of finish everything. 2 over n. We have 44 n minus 8n minus 2n. So we end up with a, and hopefully you're checking my arithmetic, 34n minus 24 minus 24. So we get minus 24, and then minus 4 is minus 28. And then here we have a minus, these each have a common denominator. This is going to become a minus 6 over n. We're almost to the end. This becomes the limit as n goes to infinity of 68. Once I distribute it, minus 56 over n minus 12 over n squared. This becomes 68 minus 0 minus 0, which just becomes 68. Okay, that does seem to me to be pretty right with what the area is. But if you're on an exam and you're like, gosh, you know, there's a lot of opportunity for error to happen, because it does happen for me too. What I recommend is just checking it using the definite integral. Most of you are more familiar or comfortable with that definite integral, so definitely feel free to check it with the definite integral. That can give you an idea of like, hey, oh, I probably did something wrong. Let me just go back and check my arithmetic and see where I made a mistake. Nothing wrong with that when you're on a test. Checking your work is great, and if you know that this is equivalent, it's perfectly reasonable to go back and check your written work. So if we just check this definite integral, we get 64x minus x to the fourth over 4, and this goes from x equals 2 to 4. So this becomes 64 times 4 minus 256 over 4 minus 128 plus 16 over 4, and I know a lot of that simplifies. And this does in fact equal 68 if you do all that arithmetic, which is what we got, which is good. Means everything worked out. But definitely check using the definite integral. As long as you show that you did in fact, use the limit process, that's what I'm looking for. You don't have to always. Do the limit process. In fact, you'll get really comfortable where you won't usually use the limit process. So then looking at these graphs, of course, you can see kind of where ours is in the region. We're looking from x equals 2 to 4. So this first graph, definitely not that case. 2 to 4, again, bottom graph, not our situation. Or excuse me, the right graph is not our situation. It does look like this first graph is actually our graph, potentially. Because it goes from 0 to 4, 2 to 4, lies under the curve. The curve shape fits, this is from 0 to 4. We don't want 0 to 4. This is from 4, basically, and above. It doesn't fit, it's not under the curve. This one isn't under the curve. So then this leftmost graph be our graph that we're looking for. The second part was to sketch the region or identify, which we did. All right, that one took a little while. Thank you. Bye.